Here, number 5e, the angular position of a point on rotating wheels given by this equation right here. So it's a function of time, I guess, right? So theta as a function of time is equal to 2 plus 4t squared plus 2t cubed, all right? Where theta is in radians and t is in seconds, and t is equal to 0, what are A, the angular position, and B, the angular velocity, and C, the angular velocity at 4 seconds, and D, calculate the angular acceleration when t is equal to 2 seconds, and E is the angular acceleration constant. That's kind of obvious. This is pretty straightforward, right? So, so let's think about angular position in part A. So they're looking for theta when angular position at t is equal to 0, right? That is equal to 2 plus 4 times 0 squared plus 2 times 0 cubed. So theta, when it is at 0 seconds, is equal to 2 radians, right? So that was pretty easy, right? All right, then, next, let's take a look at what about part B. For part B, they're asking for angular velocity. Well, omega of t is actually just a first derivative of theta of t. Therefore, if you take a derivative of this function right here, first derivative is going to be 0 because it's constant. So you're going to have 8t plus 6t squared, right? Then once you have that, they want you to evaluate this. What is the angular velocity at t is equal to 0 seconds, right? So when t is equal to 0 seconds, my omega of 0 seconds is equal to, right, 0, basically. All right. Good. Next, for part C, they want you to figure out what the omega is at 4 seconds. All right. All right, let's take a look at that. So for part C, what is the angular velocity, right, at t is equal to 4 seconds? So that is just 8 times 4 plus 6 times 4 squared, right? So what is that? That is 32 plus 6 times 16, which comes out to 128 radians per second as part C, right? And then for part D, calculate the angular acceleration. So for part D, alpha of t is equal to first derivative of the omega or second derivative of theta, which is the position, right? So that is really nothing more than just the derivative of this, which is 8 plus 12t, right? So if they want us to figure out what is the alpha of 2 seconds, right, that is simply just 8 plus 12 times 2, right? Which is 8 plus 24, or 32 radians per second squared. And for part E, is the angular acceleration constant? And the answer is no, because it definitely depends on time. It's not constant at all, right? So no, right? Alpha of t, right, is a linear, right, function that depends on time, right? Okay. All right. Good. Any questions? All right. So that was pretty easy. All right. So let's take a look at the next problem. 6 says a wheel rotates with an angular acceleration alpha, given that alpha is equal to this, right? So this is important function. So alpha of t is equal to, right, 4at cubed minus 3bt squared, where t is time and a and b are constants, right? If the wheel has an initial angular speed of omega naught, right? So that means at t is equal to 0, right? Omega naught is equal to also 0, right? Oh, okay. Well, omega naught, basically. We just have it as omega naught. Omega at t is equal to 0 is equal to omega naught, let's just say. That's what I should say. All right. So, all right. So here, A, what is the angular speed? Well, for part A, angular speed, omega of t is equal to basically integral or antiderivative of alpha of t dt, right? So if we were to do this, since this is equal to then, right, integral of, right, 4at cubed minus 3bt squared dt, right? All we have to do is integrate that. Therefore, we could say 4at to the fourth over 4 minus 3bt cubed over 3 plus c. That c itself is basically omega naught, right? So it'd be at to the fourth minus bt cubed plus omega naught is what omega of t is. Okay? All right, so what about B? For part B, the angular displacement is a function of time, right? So angular displacement is basically delta theta. So let's find the position first. You know, if you find the position, so omega is this, and if you integrate the omega, your theta of t is equal to the integral or antiderivative of omega t dt, right? Therefore, when I integrate this, which is at to the fourth minus bt cubed plus omega naught dt, right? What I have is, I have a t to the fifth over 5 minus bt to the fourth over 4 plus omega naught t plus c. The constant is theta naught, basically. Okay? Therefore, if you were to find, right, I mean, this right here itself is the function of omega, theta t, right? So theta of t is equal to, right, a t to the fifth over 5 minus b t to the fourth over 4 plus omega naught t plus theta naught. So if you want the displacement, if you want the angular displacement, then the delta theta, which is, so if I bring this to the other side, it becomes negative theta naught. So theta minus theta naught is delta theta, right? So theta minus theta naught is equal to delta theta, and that is equal to a t to the fifth over 5 minus b t to the fourth over 4 plus omega naught t would be the proper answer. Okay? Because they wanted displacement. Okay? This would be the position, and that would be the displacement. All right, then. Let's take a look at the next one. So a disk initially rotating at 120 radians per second is slowed down with a constant angular acceleration of a magnitude 4 radians per second squared. So let's write down what we know. So it's initially rotating, so omega initial, so omega naught, right, is equal to 120 radians per second. And it slows down with constant angular acceleration of magnitude. So alpha is equal to negative 4.0 radians per second squared because it's slowing down, right? How much time elapses before disk stops? So they want us to find time, right? So for part A, they want us to find time when omega final is equal to 0. Well, we know everything, right? So if we list everything that we know, so we know omega initial is equal to 120 radians per second, and we know omega final is equal to 0, and we know alpha is equal to negative 4.0 radians per second squared. They want us to figure out time. That looks like equation number 1. So omega final is equal to omega initial plus alpha t. And since this is 0 and this is 120 minus alpha, which is minus 4.0 t, right? So t is equal to negative 120. So negative 120 divided by negative 4 is 30 seconds, right? So it takes 30 seconds to come to a stop. All right. Part B. Through what angle does the disk rotate in coming to rest? So what they want to know how many angles or how much angle, right? So they want you to figure out what the delta theta is really, right? So for part B, they want you to figure out delta theta, assuming that initial theta initial is equal to 0, right? That delta theta is just the theta final then, right? We also know what? We also know that Omega initial is equal to 120 radians per second. We know alpha is equal to negative 4.0 radians per second squared. We know time now is equal to 30 seconds, right? So we could figure this out. So we know, right, delta theta is equal to omega initial t plus 1/2 alpha t squared. So delta theta is equal to omega initial is 120 times time is 30 plus 1/2 times negative 4.0 times 30 squared. All right. So if you work this thing out, you're going to get, this is going to be 3600, right? And this is going to be negative 1800. So this is 1800 radians. This is my delta theta. All right. Good. All right, next. We have a disk rotating, right, about a fixed axis starting from rest, right? So starting from rest, which means my omega initial is equal to 0, right, with constant angular acceleration. So we can use constant angular acceleration equations, right? At one time, it is rotating at 10 revolutions per second. At certain time, my omega was 10 revolutions per second, undergoing 60 more complete revolutions is angular speed. So when delta theta is equal to, right, 60 more revolutions, right, its angular speed, my omega final, happens to be 15 revolutions per second. So this, we could consider this to be our new initial. This could be our starting omega naught, all right? So be careful with this. If we have two different initials right here, and then we can use this one as our second initial. First initial is this, right? So calculate A, the angular acceleration. So we should find angular acceleration using this information right here before we use this for other ones, right? So for part A, right? So this is what's given to us from this problem, and they want us to calculate the angular acceleration. So find the angular acceleration when we know our initial omega is equal to 10 revolutions per second, or omega final happens to be 15 revolutions per second, and delta theta is equal to 60 revolutions. Now, since they gave us everything in revolutions, we don't have to convert anything because we can use revolutions and revolutions per second and revolutions per second squared, right, for constant acceleration equations, right, as long as they're consistent. Right? If they're not consistent, we cannot use the revolutions. We have to change to either radians and radians per second, or revolutions and revolutions per second. All right, then. It looks like we don't have time here. Therefore, it's probably a good idea to use equation number 2, right? If we use equation number 2, we have omega final squared is equal to omega initial squared plus 2 alpha delta theta. All Greek to me, huh? Sounds like a fraternities and sororities. All right, so here my final omega happens to be 15. Right? So 15 squared is equal to 10 squared plus 2 times alpha times 60. All right. So if you work this thing out, you're going to get 225 is equal to 100 plus 120 alpha. So 125 over 120 is equal to alpha, which is about 1.04 revolutions per second squared. So alpha is in revolutions per second squared. All right. Then for part B, the time required to complete 60 revolutions. So for part B, we're looking for time. We know everything else, right? There's so many correct ways to do it, you may get confused, right? We can use omega initial to be 10, right? Revolutions per second. Omega final is 15 revolutions per second. We know alpha now is 1.04 revolutions per second squared. So we can find time using equation number 1. So omega final is equal to omega initial plus alpha t. Therefore, 15 is equal to 10 plus 1.04, sorry, 1.04 times t. So here we have 5 over 1.04 is equal to t, and that comes out to 4.81 seconds. So it takes 4.81 seconds, starting at 10 revolutions per second, reaching 15 revolutions per second, turning 60 times. All right. Now for part C. The time required to attain 10 revolutions. Now we're looking at this part for part C, right? Now we're starting at 0 and then reaching 10 revolutions. So now we have two different initials and finals, right? So for part C, right, we have omega naught is equal to 0, and omega initial, which is like the final for the beginning, is 10 revolutions per second, right? We know angular acceleration is constant, so 1.04 revolution. Yeah, this is revolutions, right? Revolutions per second squared, right? And we're looking for time, right? We're looking for time. So here, omega is equal to, I should not have used initials and finals here. We could have used like 0, 1, 2. We could have done that, right? So, but you know what this initial means. This is, right? This is like actually the final for this. So here, if you want to, you could say omega 1, right? So we won't get confused, right? So omega 0, omega 1, right? And that is omega naught, right? Right? Omega naught plus alpha t, right? So if you want to use that, we can use omega 1 is 10, omega naught 0 plus 1.04 times t. So the time is equal to 9.62 seconds. All right, so that wasn't that bad. And what about part D? The number of revolutions from rest until the disk attains 10. Now they want to find out what the delta t 0 to 1 is, right? What the delta theta from 0 to 1, right? Which is what they want to find, right? So we know omega naught is equal to 0, right? And instead of 1, let's make it like 9.62 seconds. That'll be less confusing. All right. So we know omega naught is 0. We know alpha is equal to 1.04 revolutions per second. We know time. Time is equal to 9.62 seconds. Right? So they want us to figure out what is delta theta. How many turns does it go through? So my delta theta is equal to, right, omega naught t plus 1/2 alpha t squared. Right? So here my delta theta, right, is equal to omega naught. We know it's 0, so this whole term goes to 0, plus 1/2 times 1.04 times 9.62 squared, right? So if you work this out using your calculators, my delta theta comes out to 48.1 revolutions. So it turns a little more than 48 times to go from start of 0 to 10 revolutions per second. All right. Any questions so far? Good. All right. Let's take a look at page 7. An astronaut is being tested in a centrifuge, right? The centrifuge has a radius of 10 meters and starting rotates according to this function of theta, right? So we know here, like this is the starting, and then this is like the arm, right? And inside the chamber, right, there's a so astronaut is sitting in here, right, saying, "Get me out of here. Why am I in here? No, I don't want to be in this, right? I'm gonna puke. I'm gonna hurl." Right? So here, this is the radius, which is 10 meters, and this thing is gonna be going around in a circle, right? The theta, or the angular position function as function of time, happens to be 0.30 t squared, right? Where t is given to us in theta in radians and t's in seconds. When t is equal to 5 seconds, what are the astronaut's A, angular velocity, the linear speed, C, tangential acceleration, magnitude only, of course, because it's kind of hard to find the exact direction because it's going to be obviously tangential, and D, the radial acceleration, magnitude only. All right? All right, well, that's a lot of stuff we have to figure out. But we know this, and that's important. Okay? So for part A, they want us to figure out what angular velocity is. So for part A, what is omega? Right? When t is equal to 5 seconds. Well, omega of t is equal to theta prime of t, or the first derivative of the position function, which is 0.60 t, right? Therefore, omega of 5 seconds is equal to 0.60 times 5, which happens to be 3 radians per second. All right. Part B, what's the linear speed then? Well, for part B, V is equal to omega r. Right? So omega, which is 3.0 radians per second, times the radius of 10 meters. Now notice, at this point, the radiance just disappears magically, right? So this becomes just 30 meters per second, okay? Because radians is a fictitious unit that just holds place, right? Part C, what is the tangential acceleration? Tangential acceleration is equal to, right, alpha r. Right? Well, how do we calculate alpha? Right? So alpha is equal to first derivative of omega, or the second derivative of angular position theta. Right? So what is my alpha at 5 seconds? So that is equal to then 0.60. So alpha at 5 seconds is still going to be just 0.60 radians per second squared. Right? So what is my A tangential? My A tangential is equal to then 0.60 times 10 meters. Right? Which is 10 times 6 is just what? 6 meters per second squared. Again, the radiance just disappears, right? It disappears. And then, what about part D? What's going on with part D? Right? Well, part D asks, what is the radial acceleration, magnitude only, at 5 seconds? Right? Well, A radial is equal to v squared over r, or omega squared r. Right? Well, we already know what v is, right? And v is equal to 30 meters per second at 5 seconds, right? Square that, divide that by 10 meters. So we're going to get 90, right? 900, I mean, meters squared per second squared divided by 10 meters. Therefore, we're going to get 90 meters per second squared for my A radial. Okay. And if I were to ask you for, like, I know this wasn't asked, but part E, what is the magnitude of A total? I could ask that, right? If I ask that, then you should be, that's easy, Mr. Kim. That's simply just A radial squared plus A tangential squared. Duh, right? So you should be able to calculate that, right? Mr. Kim, you are insulting my intelligence. I laugh at your general direction, right? So if you want to, then you should be able to calculate that pretty easily. Okay. Let's see. That's like 90 squared plus 6 squared, right? Square root that sucker, and you should get somewhere around like 90.2 meters per second squared. Okay. So, yeah, I know we didn't That wasn't asked, but it's just good to know. Right? It's good to know. All right. And then, last problem. All right. So here, wheel A with radius of RA, which is 10 centimeters, is coupled by a belt B, this belt is B, to wheel C with radius of RC. Right? So RA is equal to 10 centimeters. Right? RC is equal to 25 centimeters. Okay? Wheel A increases angular speed from rest at a uniform rate of 1.6 radians per second squared. Wow, right? So alpha A is equal to, right, 1.6 radians per second squared. Determine the time required for wheel C to reach a rotational speed of 100 revolutions per minute. Well, now look at this. Here we have radians per second squared. Here we have revolutions per minute. We have mixed units here, right? We're screwed. So we have to be careful with this. So since we know omega C happens to be 100 revolutions per minute, right? We can convert this into radians per second. And to do that, we know in 1 minute there are 60 seconds, and in 1 revolution there are 2 pi radians, right? So if you work this thing out, you know you're going to get minutes canceled out and revolutions canceled out. We'll get radians per second here. So if you work it out, I think you'll get something like 10.47 radians per second as my omega C. All right. All right. Well, that's good to know. Assuming that belt does not slip, right? So that's good to know as well. But here's the crazy thing. This belt is going to keep moving at a same speed as whatever this speed is at anywhere along the belt, right? So the tangential speed or tangential velocity v of c at this point on the belt, if I were to look at this point on the belt, this tangential velocity, instantaneous tangential velocity, compare that with instantaneous tangential velocity for this. These 2 points that's placed on this belt will travel exactly at the same time. So we can say that V at point A is equal to V at point C, which is equal to, I'm just going to call that V. Okay? So, how fast is it turning? What is this V at C? Well, we know V at C is V at C is equal to omega R. Right? Omega at RC. So V at C is equal to 10.47 times RC is 25 centimeters. So if you want to keep it in centimeters, you can, but I'd rather keep it in meters, so I'm going to say 0.25 meters. Right? So V at C comes out to 2.618 meters per second. All right? That means my A, right? My AC is also, V at A is also the same value. That means my VA is 2.618 meters per second as well, at RA is equal to 0.1 meters. So since omega A is equal to VA over RA, which is equal to 2.618 divided by 0.1. Why did I switch my colors? I'm sorry. I didn't mean to switch colors. Right? Therefore, omega A happens to be 26.18 radians per second. So now we can say omega final A is equal to omega initial A squared, right? Not squared. Plus alpha AT, right? You know the initial omega is 0. So omega final, which is 226.18, is equal to alpha 1.6 times t. My t is equal to 16.4 seconds. All right, we're done. Friday, we'll be doing torque and the dynamics of rotation. All right, so hopefully you'll be ready for that. All right, if there are no questions, we're done. Have a wonderful day, everybody, and take care of yourselves. All right, bye-bye.